So we got viscosity and fluid flow. Now, what's viscosity? You already know from chemistry, like viscosity is like the thickness of a fluid. So like the thicker it is, the more difficult a fluid is able to go through a funnel, maybe. So if you had like a funnel and you put water through there versus like some old oil, the oil would take a really long time for it to flow out the funnel. Whereas with water, you just come in and come right out. So water is not very viscous, but something like sludge or oil is going to be very viscous. But what is it in terms of physics? Viscosity is the frictional force generated by the interaction between like the molecules of the fluid and the actual surface that it's making contact with. So if we had a pipe right here, the inner surface of the pipe and the molecules within the fluid, they're going to create frictional force between those two. And that's actually what viscosity is that interaction between those molecules in the fluid and the rubbing against the surface of the inner wall of your pipe. It also has to do with the surface area of the surface tension of the fluid itself. But that's how we're going to look at it. Now, how do we know when something is really viscous versus non-viscous? Well, I gave you two examples here in our drawing. If something is not viscous, then the fluid that's near the surface, the molecules that are near the surface and the molecules that are at the center, they're not going to have a very difference in their flow or in the velocity that they're moving. So the molecules that are right here of water versus or fluid, not water, doesn't have to be water. The molecules that are moving at this speed versus this speed are going to be almost nearly the same. And therefore, this isn't a very viscous fluid. Whereas something that's more viscous, the molecules in the center are going to move much faster than the molecules that are on the outer surface. The more viscous the fluid, the more difficult it is to move through the pipe. That's how you could look at it. So the more difficult or the more viscous a fluid is, the more difficult it is for that fluid to flow through that pipe. Now, another way we could look at viscosity is in terms of time. So this is viscosity as a function of time. You can see at time equals 0, all these particles are aligned exactly the same. But as time moves on, so time goes to 2, time goes to 3 seconds, to 4 seconds, 5 seconds, whatever, you can see that the particles in the middle are traveling faster than the particles on the outer perimeter. And so this is the viscosity as a function of time, as it would look. Okay, so that's that. Do I need this anymore? We can erase this. Well, so a new way of looking at pressure. So this is going to be a new way of looking at pressure. Now, pressure we've talked about in two different ways. If you change the elevation of something, like a fluid flowing through a pipe, if you change the elevation, you know that at higher elevation, the pressure will decrease as you go up in elevation or in height. The other way you could change pressure is by moving faster. If you go from a pipe that's like this big to a pipe that's this big, then the velocity of the fluid is going to increase. And when you have an increase in velocity, you will have a decrease in pressure. So that's two ways you can change pressure. Pressure can also change because of the viscosity. So whichever way the water is flowing here, if you have a very viscous fluid, you're going to have higher pressure before and lower pressure afterwards as the viscous fluid is moving. So this is the change in pressure that you're going to get. And how do we actually quantify that? How do we write that in numbers? Well, we're going to say that the change in pressure for a viscous fluid is going to be proportional. That means proportional to mu times the length of the pipe times the cross-sectional area, the radius of the opening of the pipe. So how big that opening is to the power 4. That's a 4 right there. And so the change in pressure is given roughly by this idea right here, where mu is the coefficient of viscosity. Remember, viscosity is similar to the force of friction against like two surfaces. In this case, it would be the molecules and the surface of the inner wall. So the mu that we're talking about here isn't the coefficient of friction, but it's almost exactly like it. It's the coefficient of viscosity. So depending on what the two surfaces are, will give you different coefficients of viscosity. So for example, like a pipe and oil going through a pipe, or oil going through, water going through a funnel. Their coefficients of viscosities will depend on what the fluid is and what it's traveling through. The length of the object that the fluid is flowing through and the radius of the pipe that's going through. The other thing that we can know is that the speed, V, is going to be proportional to the radius of the pipe, squared minus where you want to find the speed. So let's say you were looking at the speed right here versus right here. So R is the distance from the center moving outwards, lowercase r. It's the distance from the center and how far you're moving away from it. And depending on where you are, no pun intended, depending on where you are, the speed of the fluid is going to be different. And we know that because of this picture right here. It's going to move much faster here than there. But we can actually put numbers to that by looking at our examples. So if r was equal to lowercase r, so if this is equal to lowercase r, that means where we're looking, we are looking right here. We're looking at the speed of the flow of water or fluid right here. That's when r is equal to big R. Well, when we plug it into our equation here, it's going to be r squared minus r squared. That gives you 0. So you're not going to get a lot of speed, or you're going to get 0 speed at the surface right there. But as you move closer, if r is right at the center, you'll get the maximum velocity because it'll be r squared minus 0, which is just r squared. So that will be the maximum velocity right at the center. And as you move away, the speed of the fluid is going to be less and less and less. Okay, so that's the first one. The second question, how would you change the pressure if the pipe, what the heck did I write there? If the pipe gets narrower, I don't even know what I wrote there. So if the pipe got smaller, how would the pressure change in the pipe? Okay, so we say that the change in pressure is proportional to mu over L divided by R squared. So that's what our pressure is. And we'll call this pressure naught, the change in pressure naught. So our new pressure, P final, let's say is not R. We have to change the length of the pipe. So we're going to make this thinner. If we make this thinner, let's say by only 10%, so it's going to be 0.9 times R, and we got to put that to the power 4. If we do that, right, then this final pressure is going to be 1.524 times the original, I know I'm writing diagonals here, times the original pressure. So you can cube this thing to the power 4, and then when you multiply it by this part right here, which was just the beginning, you end up with 1.524 times the original pressure. Why is this so intriguing, at least? This number right here is where we're interested, not the 1.54, but the 0.524. The 0.524. That means that the pressure increased. So the pressure increased by 52%. The pressure from the initial to the final increased by 52%. Well, let's use an application of this. what this could show us. For people who have health problems, they have their arteries will decrease in size. So if their artery was to decrease by only 10%, if it only decreased by 10%, that means that the pressure that the heart is going to exert on the heart is going to increase by 52%. So just by clogging your arteries or whatever and making them narrower, by making your arteries narrower, you are going to increase the final pressure by 50%, or the final pressure is going to be 50% of the initial pressure. So a 10% decrease in the artery will increase a 50%, not 10%, but 50%. Your heart has to pump 50% harder. Think about that. That's nuts. So that's why it's super scary when if you're not on a healthy diet and you're eating like a lot of things with oils or a lot of things with fats in them. By decreasing your arteries like that, your heart has to work significantly harder for just a little bit of decrease. Okay, so that's that. Let's go on to the next thing. We're going to talk about viscosity some more, but before I do that, I need to erase some stuff. Hopefully you can see how this stuff applies to other fields as well. So this would be medicine right there. And medicine actually uses a lot of fluid dynamics, whether you know it or not. So syringes and all those things that they put in your body, and even ventilators, it's a flow of air that's going through them, all has to do with fluid dynamics. Okay. So viscosity, fluids, and this new thing called the Reynolds number. The Reynolds number. R-E-Y. Reynolds number. So what is the Reynolds number? It's a unitless number that tells us whether a particle traveling through a fluid will experience turbulent flow. And how would I describe turbulent flow? Turbulent flow would be like this. If you had a particle, let's say this is our pipe right here, and we got this little particle here that's traveling inside of a fluid, and if we have turbulent flow, then the flow looks something like this. It's all over the place. Okay? And so that's called turbulent flow. So the Reynolds number will give us an idea, depending on how big the number is, if we're going to get a turbulent flow, or the better one, that one that we like to study, if a particle is moving like this, and it's going to move through a flow of water that's like this. So beautiful. This is called laminar flow. Oh, hey, Helen. So this is turbulent flow, and this is laminar flow. And when you're on an airplane, let's say this is our airplane moving in whatever, in the sky, this is the one you want. When you have turbulent flow, that's when you get that turbulence in the airplane, because the airplane has to like adjust for all the turbulence that's going on. And turbulent flow is a very complicated concept to understand fully. In fact, we don't even fully understand this ourselves. Turbulent flow is part of a category of physics called chaotic systems. Okay, so it's part of this thing called chaos theory. So a little bit of fluctuation can cause a whole bunch of fluctuations here, and we can't really predict, or we don't have a really good equation for turbulent flow. For laminar flow, it's amazing. It just goes right through like nothing's happening. So that's what we want. Now, ignoring the shape of the particle, so let's assume that this is a sphere. If we assume that these are sphere particles here, and it's moving through a container of fluid, and the type of container that the fluid is moving through is a pipe, let's say, we can say this about the Reynolds number. If the Reynolds number, RE, how are we going to get this? So if RE, that's the Reynolds number, is less than 2,000, remember, Reynolds number is unitless, you're going to get laminar flow, roughly, more or less. But anything above that value, if you end up with a Reynolds number that's greater than 2,000, you will get turbulent flow. And you won't be responsible for like knowing Reynolds numbers for all the things. In the textbook, they give you different Reynolds numbers, or in the problem, they'll give you the Reynolds number. But what you have to do is understand that, oh, well, if this Reynolds number is over 2,000, I'm dealing with a turbulent flow. Maybe my answer might not be right. With the laminar flow, you can assume that, all the equations that you're going to be using work. Okay? So what is this unitless number, Reynolds number? Let's keep talking about it. Using the next problem. The Reynolds number, where do they come up with that number? So the Reynolds number, RE, is going to be roughly the ratio of the inertial force divided by the viscous flow force. So from here, you should, interpret that, oh, it's force divided by force. It's unitless, and that's what it is. What is the inertial force? The inertial force is the force that's trying to push the liquid through. So if you had a pipe right here, and you got water flowing this way, right? Water is not just going to flow randomly on its own. There has to be a force that's pushing on it. And that force that's pushing it to move in one direction or the other is called the inertial force. And the viscous force is the force that's holding the force from moving forward. So you could sort of think of the viscous force sort of like the frictional force. When you try moving a box across the surface, that's the force that you're applying is the inertial force. But because it's in contact with the ground, there's going to be a force resisting that, and that is called the viscous force. So the ratio between the force that's trying to push it through and the force that's trying to hold it back, that's where we get the Reynolds number. And it's very similar to, well, do I want to go there? I don't want to go there. I'll leave it at that. Now the equation for the Reynolds number, the actual equation for the Reynolds number, RE, is given by rho times V times L divided by, oh, how do I draw this? I'll draw it like that. That's not a mu. So maybe I'll draw it like this. There. Okay. And so, oh, actually it is mu. I apologize. That is mu. So rho is the density of the fluid. We know that. L is the length of the amount of length that the fluid is going to travel through. V is the velocity of the fluid. And mu is the thing that we had before, which is the coefficient of viscosity. So mu was the coefficient of viscosity that we had from before. And we can actually work out the units here to see that that's what it's going to turn out to be. So let's look at the units to see if we actually do get a unitless number. So the units for pressure are newtons per meter squared. Or we could write this as kilograms. That's what a newton is. Kilogram meters per second squared multiplied by 1 over meters squared. That's our units for pressure. The units for velocity are meters per second. And the units for length are just meters. And we're going to divide that by the coefficient of viscosity, which is going to be kilograms meters per second. And then what you're going to end up with the top is just kilogram meters per second. On the bottom, you have kilograms meters per second. So the units are going to be unitless. All right, the very last thing. And on Monday, Alan, if you're still here, as I mentioned, there's no lecture on Friday. All right, I'm going to take a day off. Okay. So get stoked for this one. I hope you're stoked because we're about to talk about Stokes Law. Stokes. Now, I could be wrong, but I think in math, there is also a Stokes, something Stokes. Stokes theorem? Is that a thing? Yeah. I think maybe Stokes theorem and Stokes Law come from the same Stoke. Stokes theorem and Stokes Law come from the same Stoke. Dr. Stokes. So, the drag force exerted on a spherical object as it's traveling through a viscous fluid. Here, we need a different color. Let's use brown. We're going to have some sort of pipe here. And maybe it could be open here. It doesn't have to be closed. And we're going to have a particle here. And the particle is going to fall down because of the force of your gravity. But it's going to reach a terminal velocity because we're going to be talking about drag force here. And what we want to know is what is the terminal velocity as this particle falls down this fluid here. Now, the first thing that I should mention to you is that this is laminar flow. So the Reynolds number is going to be less than 2,000. So if that's the case, then the way we're going to interpret this particle is like this. Let's put our particle, like that. There we go. Okay, so that's the flow of water. And we've got our particle right here. And it's traveling down. And here is the great contribution of Mr. Stokes. Mr. Stokes, or Dr. Stokes, said that the drag force on a particle, it has to be a spherical round particle. The round particle is going to be given by this equation right here. 6 pi times mu times r times v. So if you would think about drag force, this is kind of close to the drag force that we talked about in air, where we had, how do we write drag force? K, where all of this is actually a constant. Or I think we wrote it as v. I forget if it was k or not. And so we end up with k times v, either v to the power 1 or v to the power 2. So this is the drag force. This is the drag force for a object falling in a fluid that's in laminar flow. That was Stokes's contribution, where mu is the coefficient of viscosity, r is the radius of the sphere. R is the radius of the object, not of the pipe. So r is the radius of the sphere, and v is what we're going to be interested in. So there are 3 forces that are acting on this object here. I'm sure you can guess at least 2 of them, but maybe one of them you don't know. And the 3 forces that are going to act on this, let's draw a free body diagram for the object that's falling down. One of them is the force due to gravity. That's what's causing it to go down. The thing that's opposing it is going to be the drag force, Fd. But there is one more force that's acting on it. Because we're inside of a fluid, you're going to have a buoyant force, the buoyant force. And that's going to be trying to lift you up. That's what buoyant forces do. So that will be the force due to buoyancy. Those are our 3 forces that are acting on this object. And we want to know, our goal is to figure out what is the terminal speed. What is the terminal? So to do that, we have to write down our equation. The sum of forces equals mass times acceleration. And it's not acceleration at terminal velocity. We get the buoyant force plus the drag force minus the force due to gravity is equal to 0, and therefore the drag force, Fd, is going to equal the force due to gravity minus the buoyant force. Okay, so that's the result we get. Now, what is the drag force? Well, we already have the equation for the drag force. The drag force is given by 6 pi mu times the radius of the sphere times the velocity, but we're going to call it velocity terminal because we've made this assumption right here that there's no acceleration, so it has to reach a constant speed. And over on the other side, we have the mass of the sphere times gravity. That is the force due to gravity. And the buoyant force is the mass of the liquid that's being displaced. So when you put an object in a liquid, there's going to be liquid that's displaced. And the amount of liquid that's displaced, that's going to give us the buoyant force. So the mass of the liquid that's displaced times gravity. That is your buoyant force. So here's what we got. Now, something that we want to take into consideration is I don't want it in terms of masses. I want it in terms of density. So how can I write this in terms of density here? Well, density is equal to the mass divided by the volume. So mass of anything is equal to the density of the object times the volume of the object. Okay? And the volume of this object, of this mass right here, is going to be the exact volume of this object right here, because the volume that the object is pushing in the water with is how much volume is being displaced. So the volume of the sphere and the volume of the liquid are going to be identical, but the density of the sphere and the density of the liquid are going to be different. So here's what we end up with. 6 pi mu times r times v terminal equals the density of the solid minus the density of the liquid. And what's going to be left is going to be the volume of either one of those multiplied by g, gravity. We can clean this up a little bit more by replacing volume. We know that volume of a sphere is equal to 4/3 pi big R cubed. So instead of writing the volume here, I'm going to write it as 4/3 pi big R cubed times g. And it looks like we can get rid of one of the r's, and I think that's it. Oh, and then 6 and the 4/3 will clean up really nicely. And what we'll get is that the terminal velocity, v terminal, is going to equal 2 times the radius of the sphere squared times g, the density of the solid minus the density of the liquid, all divided by 9 times mu, the coefficient of viscosity. And so this is the terminal velocity for an object that's falling down. A pipe. So let's say there was liquid here and it was going down. Oh, you know what this could be? This is perfect. This could be poop. So this is a toilet, and you flush the toilet, and the water toilet is going to go down, and it goes in laminar flow, and there's your chunk of turd that's going down as well, and it's going to experience a drag force. So the speed of this particle, this poop, isn't going to keep on going faster and faster and faster. It's going to reach a terminal speed, and that has to do with the laminar flow. Okay, so there is. And it's brown too. It's perfect. So there is that. Is there anything else I want to say? No, I think that's it. So that's today's lesson on fluids. If you tried solving this like v as a function of time, that's a lot more difficult. We ain't touching that. Although, I don't think it's actually that much more difficult, actually. You just have to set up a differential equation and separate v as time. You could actually do that too. I don't know if you'd want to do it, but you could. You could set up just like we do with air resistance and solve v as a function of time, not just that terminal speed. Okay, so let's do it. Yeah, you do it on your own. So I'm going to call it a day here, and I'll see you on Monday. Until